Good morning, everyone. I want to welcome all of you to this seminar. For those in the room, we have exits to the left there and to the back of the room. So in case there's an emergency that we need to use those. For those online, welcome also to the seminar. Closed captions are enabled on your computers, so make sure you use them if you need to. So the Nuclear Technologies and National Security Directorate is pleased to host the presentation of Dr. Han-Gu Ju, President of the Korea Atomic Energy Research Institute, KAERI. I'm standing in for Dr. Kearns and Dr. Lauren Kowitz, the ALD for NTNS, who have already been with Dr. Ju today, but are now in other meetings. They'll be rejoining Dr. Ju sometime later in the day. The seminar is entitled Status of Advanced Reactor Development at KAERI. Dr. Ju has been leading KAERI since December 2022. Prior to his role, he was a professor of nuclear engineering at the Seoul National University, SNU, for about 18 years. He holds a BSc degree in nuclear engineering from the Seoul National University and a PhD from Purdue University. So he's actually a great colleague of us here. Dr. Ju is renowned for his contributions to computational reactor physics, including the development of the Nuclear Regulatory Commission's PARCS code and the Descartes High Fidelity Reactor Simulation Code, which advanced virtual reactor development. He's a fellow of the National Academy of Engineering in Korea, and also is a fellow of the American Nuclear Society of the US. In 2024, he received the Purdue One Outstanding Nuclear Engineer Award. Dr. Ju is a great friend of mine and also a great friend of Argonne. So I'm pleased to invite Dr. Ju to the podium to give his seminar.
Thank you, Tammy, for the kind, detailed introduction. It is my great pleasure to give you an overview of the status of the advanced reactor development at Korea Atomic Energy Research Institute, KAERI. KAERI is the sole institution in Korea performing comprehensive research in the diverse utilization of nuclear energy, radiation, and quantum beams. KAERI has developed, unlike US, where there are many entities working on the advanced development, KAERI is the only one that works on advanced reactor development. And KAERI developed this Smart 100 integral type reactor, and we obtained standard design approval last year. For non-water cooled reactors, or generation 4 reactors, we are working on sodium fast reactor called SALUS, for which the technical safety review was done by the IAEA, and we obtained the final report this February. And in addition to Smart 100 and SALUS, we are working on 3 other advanced reactors. But those 5 reactors have all different purposes. So I'm going to talk about those reactor development. I'll first talk about LWR-based SMRs, Smart 100 and ISMR. Then I will move to the non-water cooled reactors, SMRs. There are 3 types. So before talking about those 5 reactor types, I will give you an overview of the Korean nuclear power industry, which serves as the base of the advanced reactor development in Korea. In Korea, 26 nuclear power plants are now in operation. Most of them are 1 gigawatt plants. But 4 recent ones are APR 1400, whose capacity is 1.4 gigawatt, whereas some only 4 units are under 1 gigawatt. So the total capacity of the 26 power plants is just 26 gigawatts. And those 26 plants are located along the eastern coast of Korean Peninsula. There are 4 sites, but there's also 1 site in the western coast. And 4 APR 1400 are under construction in 2 sites. And the 1 old Westinghouse type and 1 Chengdu type are in permanent shutdown. It's shown as a gray icon here. So the total number of reactors, which have been built or under construction is 32. Okay, this shows the construction history of the 32 reactors in Korea. The first unit was KORI 1. It went up commercial operation in 1978, and it shut down in 2017 after 40 years of successful operation. The first generation of reactors consisting of 8 Westinghouse type and 4 Chengdu type shown in these green boxes were all constructed based on foreign technology. But in 1987, there was a nuclear power plant technology transfer contract with the combustion engineering. And since then, 12 more Korean standardized nuclear power plants or OPR 1000 were constructed. And after that, APR 1400, which is the Korea's generation 3 reactor, are being built. You can see here that the construction of 32 nuclear power plants continued without any blank here. You cannot see any blank here in this chart. And the 28 nuclear power plants which have operated provided 1/3 of the Korea's electricity. The total generation was 4.4 trillion kilowatt hour, and the share of the nuclear power in the Korea's electricity generation reached about 40% until 2005, but it dropped to 23% during the nuclear power phase-out period of the previous government. But fortunately, the share recovered the usual 30% level in this government. Because nuclear power provided a large portion of electricity in Korea at very low cost, Korea's electricity price could be kept quite low. And it enabled very rapid industrial and economic growth of Korea. So I claim that nuclear power is a vital energy to Korean industry and economy, and also to Korean people's life. This chart compares the increasing trend of nuclear power generation and the increase of the income per capita of the Korean people. This nuclear power generation shown in the orange line led in most period led the increase of capita. Nuclear power, as the nuclear power increases, the income of Korean people increased. And quite surprisingly, the nuclear power development started quite early in Korea, thanks to the extraordinary vision of our first president, Syngman Rhee. In 1959, only 6 years after the termination of Korean War, Trigger Mark II reactor has been built, started to build with the establishment of KAERI. And in 1979, Korea 1 went operational, and 11 more nuclear plants were constructed. And nuclear technology transfer from combustion engineering was carried out during the period of 1987 through 1990. And a group of KAERI engineers, 44 KAERI engineers, were dispatched to the combustion engineering site, Connecticut site in December 1986. I myself was one of the 44 members of the technology transfer team, and I'm very proud of being member of those 44 members at the time. And those technology transfer and the continued construction of the OPR 1000 or Korean standardized plant became the basis of the development of the APR 1400 reactor. And you might notice that the export of APR 1400 to UAE was done in 2009, and all those 4 reactors are now operational in UAE. On the other hand, KAERI constructed its own multipurpose research reactor Hanaro in 1995, and the construction and operation of the Hanaro reactor became the basis of the export of a JRTR, Jordan Research and Test Reactor, in 2016. Thanks to the continuous construction of the more than, in fact, 36 plants, including those 4 units in UAE, Korea was able to build self-sufficient and complete nuclear power plant supply system. This chart shows the companies involved in the supply system. Of these 5 companies, KEPCO Engineering Construction, KEPCO Nuclear Fuel, KEPCO Plant Services, a subsidiary of KEPCO, Korea Power Electric Company, which is state-owned. The utility company, KHNP, Korea Hydro and Nuclear Power Company, is also state-owned. But the major nuclear component vendor, Doosan Enerbility, and the construction companies such as Hyundai Construction are all private. Now let me talk about the advanced reactor development programs of Korea. As I said earlier, KAERI is the sole institution who has the responsibility and capability of advanced reactor development. And KAERI is doing both water-cooled SMR development and also non-water-cooled SMR development. For water-cooled reactor development, SMART 100, which is an already developed integral type water-cooled reactor. As I said, the standard design approval was already obtained. ISMR is an enhanced version of SMART. It's also a light water-cooled integral type reactor, but with a higher capacity. SMART 100 has 110 megawatt. This ISMR is 680 megawatt, which consists of 4 modules of 170 megawatts. And this size, 680 megawatt, is adequate to replace coal power plants. So it's a mid-sized reactor. Regarding the non-water-cooled reactor or generation 4 reactors, we are working on 3 types. First one is sodium fast reactor, SFR, which targets long-term operation with the transmutation. And the second is gas-cooled reactor, which GCR, which targets for industrial heat supply. And the third one is molten salt reactor, MSR, which is targeting for maritime system of application or ship propulsion. So all those 5 types have all different purposes or usages. SMART, which stands for System Integrated Modular Advanced Reactor, is an integral type reactor in which all the major components like reactor core, coolant pump, steam generators are all integrated into one vessel in order to prevent the potential leak in the coolant pipes to enhance the safety. The original SMART, the development was started in 1997 with a capacity of 100 megawatts. And the standard design approval of the original SMART was obtained quite early in 2012. To cope with the increased safety demand due to the Fukushima accident, safety enhancement research was performed for SMART during the period of 2012 and 2016. And in 2016, Saudi Arabia and Korea agreed on the development of a SMART 100 as an enhanced version of SMART with a bigger capacity for electricity generation and also for desalination in the remote coastal cities of Saudi Arabia. And the joint project was named Pre-Project Engineering, targeting the actual construction in Saudi Arabia. And it has many, SMART 100 has many innovative features, but the most important one is fully passive safe system, shown as here. So with this fully safe system, the reactor can be in a safe state without any operator intervention for a long time. And it gives the resilience of the reactor to the possible malfunctions in accident conditions. To verify those safety of the SMART 100, the system component and design tools for licensing, the comprehensive validation experiments were performed. The first one is the fuel performance test. Second is the component mechanics validation. And third one is the individual thermohydraulics experiment for each safety system. And the third one is the integral test loop experiment. And we also built a main control room simulator, and the performance of the control system was confirmed. So in fact, we invested a lot of funding for the validation, and that becomes the basis of the application for standard design approval. Without those experimental proof, we wouldn't get the approval of the design. So in order to get the certificate of the SMART 100 design, so-called the standard design approval was tried as a joint effort between KAERI and Saudi Arabia's KAERI. And we submitted the licensing documents in December 2019. And the Korean nuclear regulator, Nuclear Safety and Security Commission, Nuclear NSSC, they started the review of the application in August 2021. And they reviewed our application very thoroughly and raised more than 25 technical questions. So the question and answer lasted more than 3 years. And finally, NSSC granted SDA in September last year. They look at all the safety components shown here. So the review process was a tedious process. It took quite a long time. This chart shows the development history of a SMART 100, which was fully licensed 2 times. And the manufacturability of SMART 100 was confirmed by the Korean nuclear vendor, Doosan Enerbility. So with the SDA and the manufacturability confirmed, we can say that SMART 100 is immediately deployable SMR, and the capacity of 100 or 110 megawatt is adequate for data centers and small grids, small isolated grids. And also it is adequate for mining sites, such as sand oil extraction in Alberta, Canada. And KAERI is now seeking business partners who can develop project to actually build Smart 100. ISMR is an innovative SMR with the goal of further enhancing the economics and the safety of smart by increasing the reactor size and also by adopting innovative technologies. So ISMR consists of four multiple modules, up to 4, and the size might depend on the demand. And all the reactor components, reactor core, steam generator, pumps, and even the control rod driving mechanisms are all integrated into one reactor pressure vessel in order to enhance the safety and also efficiency. So the in-vessel CRDM, in-vessel within vessel, that is a very unique feature of ISMR. And another unique feature of ISMR is the steel containment, which is to retain the potential water leak inside the containment and to enable pass-through reactor cooling. With the fully passive safety system, ISMR can withstand more than a week without any external power or any operator intervention. And innovative manufacturing technologies like powder metallurgy, 3D printing, and electron beam welding, and others will be applied to reduce the construction time of ISMR. And this shows the roadmap of development and licensing and the construction of ISMR. The primary milestone is to obtain standard design approval by the end of 2028. The second milestone is to obtain operation permit for a site in Korea by the end of 2034. And the currently focus is on finalizing the standard design. The design was performed already quite a lot, but we need to finalize the design to prepare the standard safety analysis report by the end of this year. And also, pre-licensing review are being performed by NSS people to see the licensability of the innovative features of ISMR. But we have to submit the so-called PISA by the end of this year, to allow 2 or 3 years for NSSC to review the innovative designs to obtain the SDA by end of 2028. And currently, there are several project efforts are being made, for example, including collaboration with the private companies or municipal government, or the investment attractions and site selection. Those are also being carried out in parallel. Now let me talk about the sodium fast reactor development. KAERI has been working on the design of various sodium fast reactor since 1990s. Kaliber 600 is the first output. The design was completed in 2007. And Kaliber 600 is a full type reactor with metal fuel, targeting transmutation, TRU transmutation with the pyroprocessing. And the conceptual design of Kaliber 600 was done in 2007, and the prototype, technical demonstrator of Kaliber 600 is called PGSFR, prototype generation 4 SFR, was done. The engineering design was done with a very close collaboration with the Argonne engineers. That was done in 2020. And now, as a spin-off of PGSFR, we developed the Salus 100 reactor.
11 a.m. It will be in conference room R150. Thank you.
With the target of long cycle operation. SALUS, that which stands for Small Advanced Long Cycle Ultimate Safe SFR, is also an integral pool type SFR with a metallic alloy fuel and FC92 cladding. To assure long time operation. 20-year cycle was possible by using special new cladding material FC92, which stands for 9 chrome and 2 tungsten, and we also have a chrome coating inside the cladding, so that long time operation is possible. And the outlet temperature of SALUS is 510 degrees Celsius, so that high temperature application of SFR is also possible. And it has a passive safety system to allow long-term cooling with special decay heat removal systems. And like the Smart 100, we had gone through very intensive verification program for SALUS 100. For example, fuel irradiation test was performed on the fast spectrum. Also, we built very large sodium coolant loop called Stella for component-wise and system-wise thermohydraulic experiment. And we generated separate effect and integral effect data a lot, and a lab-to-lab collaboration will be performed in the Argonne on the Stella experiment. And one of the reasons for my visit is to talk about the details of lab-to-lab collaboration on Stella experiment. Argonne people will use their multidimensional tool for the simulation of the Stella, which has the flow in the pool that needs 3D modeling, and Argonne has, for example, NEC 5000, those advanced tool, and we'll provide the simulation data, and Argonne will do the simulation. We also have component-wise safety code, so we'll use our code to compare with Argonne's data. The design safety report was prepared for the technical safety review by the IAEA people last December. The purpose of technical safety review is to identify key regulatory issues to avoid or minimize the risk that might be encountered during the actual licensing phase. The expert at IAEA reviewed our report to see if our design complies with the international requirement and standard. And also they look at the safety concerns and potential issues for licensing. And after very intense technical discussions, their recommendations and results were documented in the final report issued this February. And note that this technical safety review was the first one done by IAEA for non-water-cooled reactors. And these are some of the recommendations by IAEA. For example, they suggested so-called practical elimination approaches, and also they recommended establishment of the method for identifying and evaluating severe scenarios. Anyway, those recommendations will be incorporated in the further improvement of SALUS 100 design for actual construction. And to help realize SMRs, or the advanced reactors, by year 2030s, so-called public-private partnership. The concept of public-private partnership was introduced in Korea as well, the similar thing to ARDP. And in particular, Hyundai Engineering and Construction Company is interested in having their own brand of SFL-based SMR, to be an independent global SMR supplier. They are willing to invest in the development from the beginning. In that regard, KAERI and Hyundai Engineering and Construction. In fact, the company, Hyundai, they had been involved in the construction of Korean nuclear power plant for more than 50 years without any blank here, so that they are very familiar with nuclear power plant, and they have affection to nuclear power plant business. So we had an MOU with the Hyundai Construction, and for them to participate in the new government-led SFR development project. It was supposed to be started this year, but there was some issue, budget issue raised by opposition party last year, so it is postponed to next year. Anyway, in the new development, which will improve the SALUS design, all the recommendations made by the IAEA, TSR will be incorporated. Now, let me move to the topic of high temperature gas-cooled reactor. KAERI has been involved in the development of the high temperature gas-cooled reactor for hydrogen production from year 2004. And one of the major outcomes is the computational tools and modeling technologies. For example, we developed top code for the design of gas-cooled reactor, neutronic design, and the core TH code and safety analysis code called Gamma, and TRISO performance analysis code. Those among these codes, the Descartes cup and Gamma were used in the design of the MMR of the USNC's core. The USNC's core. And for the hardware side, we also built TRISO manufacturing facility at lab scale, and we produced fuel compact and performed irradiation test in Hanaru reactor. We compiled a lot of material database for graphite and nickel alloy base and others. And we also built high temperature helium loop, which can be used for high temperature steam electrolysis. The temperature can be higher than 900 degrees C, and the actual HTSE operation for hydrogen production using steam electrolysis were performed. And last year, the public-private partnership project for developing an HTGR was launched with the participation of many private companies such as POSCO Engineering Construction, SK Ecoplant, and Lotte Chemical. They formed a consortium to work with the KAERI team. And the target, the objective is to design a target plant with the 900 megawatt thermal, graphite moderated, and helium using helium current. The small reactor was named HECPA. I made this name. Helium cooled thermal applications reactor. And POSCO ENC is interested in building and selling Hectare. And KAERI will be responsible for the reactor design and lead the entire project. And POSCO ENC will design the BOC, balance of plant, BOP, balance of plant. And SK Ecoplant is interested in using this Hectare for hydrogen production using SOEC, solid oxide electrolysis cell. And Lotte Chemical is interested in using building process heat system for chemical industry. Current budget is secured. 32 million US dollar is secured for 4 years. It's not much, but it will increase. Currently, the share between government and private is 17 versus $15 million. The share of the private contribution will increase as the project moves on. The target is to submit PISA by 2029 and start construction in 2034. And the budget will increase. Now, the last topic is the molten salt reactor. We have good names. It's Eureka. But the progress is not much, but the name is good. Ultimate reactor for efficient carbon-free applications. The advantage of molten salt reactor is that it can be made simple and small due to the fact that fuel is mixed with a coolant salt. So it is adequate for ship propulsion application. And it is expected that it will be safe because in case of accident, if there is a leak of salt, it can be solidified quickly so that no significant dispersion of radioactive material will happen. So it is considered to be safe. But there is a very important concern about corrosion. So the corrosion problem needs to be resolved. And there should be many experimental facilities to prove and improve the corrosion problem. And we are considering to build molten salt facilities in our new campus. We are building a new campus in the eastern coast area called Campo. But the budget, current budget, assigned budget for MSL development is not sufficient. Only $29 million for 3.5 years are secured. But to build those experimental facilities, we need a lot more investment. So currently, so-called preliminary feasibility study examination of the large government investment is the preparation for the documents is being done. If it is accepted, we build experiment facilities at the campus site. And the target for MSL development is to finish basic design and application by 2035. Now let me conclude. Continuous construction of 32 nuclear power plants for more than 50 years provide the self-sufficient and independent nuclear power plant supply system in Korea. With the R&Ds of various new reactors being paralleled by the construction, the nuclear power technology is well established in Korea. And various advanced reactors are under development in the road to carbon neutrality. Those all have different usage or different purposes. SMART is for small grid and data centers. And ISMR is primarily to replace coal power plants. And SALUS is for long-term operation in remote places. And Hectare is an HTR for high temperature industrial heat supply and also for hydrogen production. And Eureka is MSR, which is for ship propulsion. As you might notice, the Hector and Eureka, the investment and development efforts, not so much, but the other three, we made big progress with a lot of investment. Anyway, close collaboration with private entities and also international cooperation like Argonne is strongly required for actual realization of advanced reactors. Thank you for your attention.
Thank you, Dr. Ju, for the excellent exposition on the great work being done at KAERI. Now, this gives us the opportunity to ask him questions, both for people in the room, who I really appreciate you folks coming out for this session, for this seminar, and also for people online. We have a lot of people online. So we'll try to see if any questions in the room, and if not, we'll go to the online. We'll alternate between the room and online. Okay.